Hi everyone, today we're going to start our unit on probability. And so to kick off the unit, we need to discuss something called a sample space. So a sample space of an experiment is the set of all possible outcomes. And when you're finding probability of things, you're finding probability of events that happen in an experiment. So if you roll a pair of dice, then that's an experiment. If you draw a card out of a deck, that's an experiment. So the sample space of an experiment is the set of all possible outcomes. For example, if I roll a single six-sided die with numbers 1, 2, 3, 4, 5, 6 on the outsides of each face, and it lands on 1, then the experiment is rolling the die. The sample space is the set of all possible outcomes. So 1, 2, 3, 4, 5, 6. And a certain event that I'm looking for, my desired outcome, maybe I'm looking for rolling a 1 or rolling an even number, so a 2, 4, or 6. So that would be desired outcomes. But a sample space of an experiment is the set of all possible outcomes that you could have while performing the experiment. A sample space can be represented by using an organized list, a table, or a tree diagram. So example 1 says represent the sample space, all of the possible outcomes for an experiment, by making an organized list, a table, and a tree diagram. So the situation is that the baseball team can wear blue or white shorts with blue or white pants. So I need to generate the sample space of all possible outcomes for what this baseball team can wear. So let's start out with a table. A table for the shirts, I can either wear, well, I say I'm not on the baseball team. The baseball team can either wear blue shirts or white shirts. For the pants, the baseball team can either wear blue pants or white pants. If you think back to like multiplying polynomials or a Punnett square in biology, whenever you're doing gene sequencing and finding all the combinations of genes that you can have in offspring, this kind of looks like the same thing. So we could either have the baseball team wear blue shirt, blue pants. I'm going to say blue S, blue P. Or we can have them wear a white shirt, blue pants. White shirt, blue pants. We could have them wear a blue shirt, white pants. Blue shirt, white pants, or we could have them wear white and white. So white shirt and pants. So these are all of the possible combinations in my experiment. And the experiment is picking what the baseball team is wearing. What's their jersey? What's their uniform? So this is the sample space. There are 4 items in there, 4 different combinations of shirts and pants. So let's move to a tree diagram. To represent this same information, you start out by picking one of the pieces of your experiment. So let's start out with shirts. Either the baseball team can wear blue shirt or the baseball team can wear white shirts. And then from there, each team has the option of 2 different pairs of pants. So blue pants or, white pants. If they wear a white shirt, they still have the same 2 options for pants. Blue pants, white pants. So your probability of picking a particular outfit kind of follows the line. So if I'm looking for white shirt, blue pants, well, that outcome is here. White shirt, follow the line, blue pants. Maybe I'm looking for Blue shirt, blue pants. So I would follow the line here and here. And that is an outcome. Blue shirt, blue pants. So you kind of follow the lines in a tree diagram. And then finally, an organized list is just listing out all of the possible outcomes for this experiment. So either the baseball team can wear blue shirt and blue pants, or blue shirt and white pants. They could wear a white shirt and blue pants, or they could wear a white shirt and white pants. So those are the possibilities, and we just listed them out in a string of possibilities, our list. So this is a sample space. The sample space has 4 possible outcomes, 4 paths to follow here, 4 items or pairs listed in the organized list. So that's a sample space of your experiment. Now, the fundamental counting principle is the number of all possible outcomes for an experiment, and it can be found by multiplying the number of possible outcomes from each event or choice. So you can use the fundamental counting principle to find the number of all possible outcomes for an experiment by multiplying the number of possible outcomes for each event or choice. So remember, before, our sample space for this baseball team experiment, picking the outfit, our sample space had 4 items. Well, there were 2 shirt options and there were 2 pants options. So the fundamental counting principle says that I can find the total number in the sample space by taking my 2 shirt options and multiplying it by the 2 shirt options, or 2 pants options. So that's 4 total options. And that's 4 items in the sample space, which is exactly what we came up with. So let's move to example 2 to talk a little bit more about the fundamental counting principle. It says find the number of possible outcomes. That implies that you're going to be using fundamental counting principle for each situation. And it says a room is decorated with one of each choice from each category. So we have, for the bedroom decor, 8 paint colors, 6 comforter sets, 8 sheet sets, 5 throw rugs, 3 lamps, 5 wall hangings. It's a lot of options, and we need the total number of outcomes. So I don't just want to add these up, because what if I choose paint color number 1 with comforter set number 2, or comforter set number 3? Or what if I choose paint color number 1 with comforter set number 3, and I can't decide between the sheet sets? So I pick either 1 or 4 or 7. So whenever I'm trying to find the total outcomes, I need to use the fundamental counting principle. So I want to multiply all the possible outcomes from each event or choice, and these are all of the choices. So I have 8 paint colors. I want to multiply it by 6 comforter sets. I've got 8 sheet sets. I've got 5 choices of throw rug, 3 choices of lamps, and 5 choices of wall hangings. So when I multiply these together, that's 48 times 40 times 15. 48 times 40 is 1,920. And if I multiply by 15, that's 28,800 total outcomes. And these are items in the sample space. So I'm going to go ahead and fill in 28,800. That's the number of choices, because for every paint color, you can choose a comforter set and a sheet set and a throw rug. And even if you change one thing to be different, then that means that you've created this new outcome for the bedroom. There are a lot of options. So let's go on to the second page. Second page starts out with part B. It says you flip a coin 4 times and you spin a spinner with 3 regions twice. Okay, so this is the experiment. We flip a coin 4 times, see what we get, and we spin a spinner with 3 regions twice. And when we say spin a spinner with 3 regions, that means maybe it's a circle, and maybe we have 3 regions. So 1, 2, 3, something like that. So if you flip a coin 4 times, when you flip a coin, how many outcomes are possible? You can either get heads or tails. So there's 2 outcomes. If you flip a coin 4 times, then those 2 outcomes are reoccurring every time you flip the coin. So we've got 2 times 2 times 2 times 2. This is your 4 times. Because every time you flip that coin, either you can get heads or tails, and then heads or tails again, and then heads or tails again, and then heads or tails again. When you spin a spinner with 3 regions twice, you've got 3 possible outcomes. You could land in this first space, second space, or third space. So 3 outcomes. But when you respin the spinner that second time, you still have the possibility of all 3 outcomes. So you want to multiply this by 3 and by 3 because that's the 2 times that you spin that spinner. So when I multiply these together, 2 times 2 is 4, 2 times 2 is 4, 3 times 3 is 9. That's 4 times 36. That's 144 possible outcomes in the sample space. Okay, let's look at part C. You roll a 6-sided die 5 times, and you flip a coin 4 times. So think about it. How many outcomes are there when you roll a 6-sided die? There are 6 outcomes. You can either roll a 1, 2, 3, 4, 5, or 6. That's 6 possible outcomes. And we do it 5 times. So that means that every time we roll the die, there are 6 outcomes, and then 6 outcomes, and then 6 outcomes. 5 times, right? If you flip a coin, how many possible outcomes are there? Well, there's heads or tails, so there's 2 outcomes. But you do it 4 times, so every time you do it, there are 2 possible outcomes. So we need to multiply by 2 4 times. So what I'm finding here is like, maybe I'm looking to find the probability of getting heads, heads, tails, heads, tails. Oh, sorry, this is a die. Maybe I'm finding the event rolling a 1, 3, 1, 1, 6, heads, heads, tails, tails. So maybe I'm looking for that particular string of outcomes in my experiment. So when I multiply these together, the number of total outcomes, let's see, we've got 36 times 36 times 6 times 2 to the power of 4, which is 16. So we've got 124,416 outcomes in the sample space. It's a lot of outcomes. And most of the time we're just looking for one in particular. Maybe rolling a 5, 5, 5, 5, 5, heads, 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 heads. And that's one of the outcomes out of this many. So that's a lot. So let's look at basic probability. The basic probability of an event occurring, so maybe rolling a 5, 5, 5, 5, 5, heads, 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 heads. The basic probability of an event occurring can be found by determining the number of desired events in relation to the total number of possibilities or outcomes. We express probabilities as ratios, which is a fraction, but we express it in decimal form, which some of you are probably going to be pretty excited about. So basic probability is found by determining the number of desired events in a relation to the total number of outcomes. And that total number of outcomes is what we were finding here with the fundamental counting principle. So we're going to create a ratio for that, and then we're going to turn it into a decimal. So example 3, determine the probability of each of the following. I want to find the probability of rolling a 1 on a 6-sided die. So rolling a 1, that's my desired event. And there's only one 1 on the die. Now, the possible outcomes is how many outcomes you have on this 6-sided die. Well, on the 6-sided die, the possibility is 1 or 2 or 3 or 4 or 5 or 6. That's what you can roll on a die. And so there are 1, 2, 3, 4, 5, 6 outcomes. So that fraction that we create is 1 over 6, and if you turn it into a decimal, then you end up with 0.167. And this is the probability of rolling a 1 on a 6-sided die. Notice that I rounded to the nearest thousandth. This number is really 0.166, and the 6 is repeating, but we rounded to the nearest thousandth here. All right, let's look at part B. I want the probability of rolling an even number on a die, so the same die. If you are rolling an even number, the only options are 2 and 4 and 6. You may think 8 and 10 and so on, but remember this is on a die, and the only options on the die are 1, 2, 3, 4, 5, 6. So the even numbers are 2, 4, and 6. So the desired event is either rolling a 2, a 4, or a 6. So there are 3 possible desired events. The number of possible outcomes, the total number of outcomes, there are 6 outcomes. So that creates the fraction 3 over 6, which is really 1/2, which is really 0.5. So the probability of rolling an even number on a die is 0.5. Now, before we move on to the last page, I want to make sure that we kind of introduce a little bit of a notation here. So when we talk about the probability of something, we usually write it kind of like a function. So probability is P of something. This stands for probability. So here I wanted the probability of rolling a 1. So the probability of, and then the desired event goes in here, a 1, equals 0.167. Same thing here. The probability of rolling an even number, we would say the probability of a 2, a 4, or a 6. That's 0.5. We could have also written the probability of, and then we could have abbreviated the event to even, like even number, and it would equal 0.5. So let's move on to our last page. We have a few more examples. So in this last page, there are 24 marbles in a bag. There are 6 blue, 4 red, 8 are green, and 6 are yellow. What is the probability of drawing a red marble? So remember, we want the desired, so the number of desired, and then we want the total outcomes, the possible outcomes, and that will help create our fraction. So what do we desire? Well, we desire a red marble. So looking in the bag, we've got 6 blue, 8 green, 6 yellow, but 4 of them are red. So there are 4 possible marbles that are what we desire. The total outcomes, well, there are 24 marbles in the bag. So 24 is my sample space. 6 blue, 4 red, 8 green, and 6 are yellow. So we've got 4 red marbles out of 24 possible marbles. So that creates the fraction 4 over 24, which is 1 over 6, which is the same thing as our probability of rolling a 1 on a die, 0.167. So we would write this as the probability of drawing a red marble equals 0.167. In part D, we're using the same bag as before, so the description up here is the same in D. What about drawing a blue or yellow marble? So the number of outcomes doesn't change. There are still 24 marbles in the bag. However, this time the desired is blue or yellow. There are 6 blue marbles and 6 yellow marbles. So total, there are 12 possible marbles that we could draw here that are what we want, they're what we desire. The outcomes, there are still 24 marbles in the bag. So when you create the fraction, 6 blue and 6 yellow make 12 total desired marbles out of 24. That simplifies to 1/2, which is 0.5. So the probability of blue or yellow is 0.5. Okay, so let's look down to part E. There are 4 gumballs, 6 sour candies, and 8 chocolate candies in a bag. What is the probability that you draw not a gumball? So desired. If I don't want a gumball, I'll take anything other than a gumball. So I'll take not this, but I'll take 6 sour candies, or I'll take 8 chocolate candies, but I don't want any of the 4 gumballs. And the total number of outcomes that are possible is 4 and 6 and 8 altogether. So 4 plus 6, which is 10, plus 8, which is 18. So my probability of drawing not a gumball would be 6 plus 8, that's 14, over 4 plus 6 plus 8, which is 18. If you simplify that, you get 7/9. And if you put that in form of a decimal rounded to the nearest thousandth, that's 0.778. So we were finding the probability of not a gumball. That was 0.778. So what I'd like for you to do, since we've been doing all of these kind of together, I'd like for you to pause your video and try problem F. It says, using the same bag of candy as before, as in part E, what is the probability that you draw a gumball or a sour candy? So pretend like you're drawing out a gumball or a sour candy and find the probability of that event. So in that same bag of candy, there are 4 gumballs and 6 sour candies. So those are our total desired things that we could draw. The outcomes is still 18. 4 plus 6 plus 8 is 18. So we get a fraction that we simplify and then we turn into a decimal. So the probability of drawing a gumball or a sour candy out of that bag of candy is 0.556.